Hello, everyone. This is Ziqiang from Fujitsu R&D Center. Today, I will present our recent work on image restoration. It is based on the conditional velocity score estimation. This is joint work with Rujie from the same institution. Thirdly, I will introduce the background of this work. The target of our work is that to renew the high quality and universal low-level image restoration, and in this task, we want to recover the original clean image from the degraded images. The degradation may be due to the blurring, low resolution, occlusion, or some kind of nonlinear transformation, for example, the face retrieval. Our approach is based on the generative models, and you know that the diffusion generative models has been very popular, a very powerful method in generation tasks. For example, text to image and speech synthesis or 3D model synthesis. So it has been used in has been successful in many tasks, and also it has been make success in image restoration. There are two kind of framework to use DGM in the image restoration. They are zero shot, and the second one is the supervised image to image translation. For the image translation task framework, it needed to train separately for each task. For example, if it trained on inpainting task when the inpaint block is in the center, then when it is applied to the different kind of inpainting tasks, it cannot work very well. So image-to-image translation framework is not universal and cannot be applied to other tasks. And so we put our method based on the zero-shot image restoration. For the principle behind the zero-shot image restoration is to use DGM as the prior distribution for real images, and to use the degraded image as a kind of conditional input to inject into the generative models to control the path of diffusion. I mean that it can refine the prior distribution to the posterior distribution of the ground truth. Then when we can recover the clean image from the degraded images. So there are two kind of schemes in the zero-shot methods. I mean that replacement-based and reconstruction-based. Replacement-based method is to add a degraded signal to the predictions on the diffusion path, while the reconstruction-based is to minimizing the error between the original and the constructed degraded signal. Example, DDRM and DPS. But this method only carry out in the position space, lacking the modeling of the velocity of the image on the restoration path. And there is indeed we can model the velocity and positions together in the diffusion path. For example, the critically damped energy diffusion model can model these two variables together. The position and the velocity of the image can be diffused and cupped and affect each other together, and they can smoothly converge to a equally beam data distribution without oscillation. You can see that here is the example. This is the standard one order or first order STE. You can see this color, the diffusion path is oscillation a lot, but for the second order SDE, I mean that the position and velocity SDE CRD, the diffusion path is very smooth compared to the previous one. So this is the so it can converge to the equilibrium, and it also can enhance the generative or restoration effect, since there are more. It can control the diffusion paths more accurately. So we build our model based on the CRD. This is our method. Our idea behind our method is very easy. We inject the degraded image into the reverse CRD generation process and control the diffusion path. And the difficulty is that the computation of CVS is very hard, and we can only convert it into a sum of UNS. I mean the unconditional score and observation related score. The UNS can be obtained by a general pre-trained CRD model on the images. And the OVS is intractable since there is no direct connection between the current state and the degraded movement. They can only connected by the initial state, since you know that current state and initial state are connected by the probability transition with the diffusion models, and also that the initial state and the movement can be connected by the problem formulation of the restoration, and so if we can put x0 in this equation, we can connect this all together. So the problem can be attributed to estimation the mean of the initial image from the current moment. Luckily, we came out a close formulation of the estimation of this initial state. So all this the CVS can be computed based on this formulation, and this is an example of our diffusion in the restoration path. The first row shows the evolution of position, and the second row shows the evolution of velocity. You can see at firstly, when in the initial state, the velocity is very random, but at the last stage, the velocity can control. Is very clear how the position needed to move to the target image. Next, I will show the result of our method. We have conducted experiments on 4 datasets, and on three kind of tasks, but in 7 subtasks. 3 tasks are linear, nonlinear, and blind restoration. And we has compared our method with very competitive approaches. They are DDRM, DPS, MCG, and IRVR. And metrics we used are PSNR, SSIM, and FID. The qualitative results is very encouraging and very compared to the previous SOTA of, the DPS. On the linear task, there will be 50% increase in SSIM and 10% of decrease in FID. On the nonlinear task, we have 50% in SSIM and 40% increase in PSNR. So the quantitative results is very encouraging, and also we have some qualitative results. We have conducted the restoration on faces, dogs, and some products in self-checkout. So I mean that this image restoration can be used in self-checkout due to the, for example, quick and complex self-checkout due to there are maybe motion blurring or occlusion of product. This can be used as a pre-processing for self-checkout. So this is all my presentation. Thank you.